Okay, let's talk about polygonal modeling. This is going to be the most fundamental skill that you will learn to make work with 3D tools. Okay, so this is an example of the simplest polygon you can have, a triangle. And it has 3 points or vertices, 3 edges, and a face, or the area that is contained within the edges and points. Typically, a polygon and a face are considered to be the same thing, so those terms can be interchangeable. A vertice essentially is at each corner of your polygon. It contains X, Y, and Z information, which is why it's called 3D animation, because those X, Y, and Z coordinates are in 3D space. They can contain other information as well. There are also edges that you can use to more easily manipulate where the vertices are in 3D space. Edges can also help you describe how sharp or smooth contours are of an object. And then faces, or the polygon, or polygons, essentially on a triangle are going to be flat, and hopefully will be relatively flat on most of the polygons that you create. If you start creating too many points on your polygons and moving them too far apart in one dimension or another, and they start to become non-planar or not very flat, you'll get really unexpected rendering results. So a lot of this is to be able to predict what the outcome is going to be. You want your polygons to be fairly planar. There are 3 types of polygons that we're going to talk about: triangles, quads, n-gons. An n-gon is essentially anything with 5 or more sides. A quad is typically what you want to aim to use when you're making your polygonal meshes. All of the tools are designed to work well with quads. A lot of the tools will break or not function as expected when trying to use them with triangles. Quads are going to allow you to create what's called edge flow, or have really nice geometry. Again, the tools are designed for quads, so try to use them as much as you can. No matter what you use, it always eventually becomes a triangle. So quad is just 2 triangles, and an n-gon is n number of triangles. But essentially, you want to predict or control where those 2 triangles are going to meet, and the software is going to decide for you. So the less planar your polygon, the more unpredictable the shape of that polygon might be. Okay, so this is a normal, and a normal is essentially the front face of the polygon. A polygon is a front and a back. If your polygon is flipped around, you will see all sorts of rendering issues when you go to create your images. The shader algorithms need that normal information in a particular way so it knows how to communicate what you're trying to communicate. If it's a smooth surface, or if it has a hole in it, or whatever, if that polygon is not facing the right way, it's not going to look right. So these generate what are called artifacts. So we'll take a look at what those artifacts are on a polygonal mesh. So on the left-hand side, you can see a shading artifact. It's sort of a darker square on the mesh. And on the right-hand side, I kind of show what I did to create that. I created a flipped normal where I faced the polygon the wrong way. The shading algorithm, again, didn't know how that surface is supposed to look. So a lot of times when you're getting issues in your renders, it's because the normals just need to be corrected. Here's another example. You may have 2 pieces of geometry overlapping. You may have a duplicate. It's really easy to accidentally make duplicates using 3D tools. So a lot of times you just need to delete that duplicate and you'll fix your issue. So topology is essentially the wireframe or the structure of your 3D model. And you can have different topologies, but essentially create the same shape object. So in the image to the bottom right here, we can see a low resolution mesh, And then on the left-hand side of that image, we can see the final result. The high-resolution mesh in the middle produces that same object. The difference is we are using more polygons to describe that object. It's not very efficient in our case here to be using this many polygons. We just don't have that detail to require all of that extra geometry. So the process of retopologizing is essentially the process that aims to reduce the amount of polygons used to describe a particular shape of an object. This is going to be really important in something like a game engine. Okay, so I have here an example of mesh subdivisions. Subdivision is a mathematical calculation where essentially more geometry can be added to a mesh at the click of a button. So as we add subdivisions from left to right, the original mesh being on the left, and then we have level 1, level 2, and level 3. Level 3 is going to be the smoothest, highest quality, but we are getting round corners and things like that. So as you add subdivisions, it is going to change the topology of your object. So just keep that in mind. Subdivisions are typically calculated using the Catmull-Clark algorithm. Those are two people from computing graphics history who came up with the math to be able to accomplish this. So now we have an example of an end-pole. An end-pole is a point with 3 edges, and it's usually at a corner. And when you add subdivisions, what you have is a gathering of mesh density called pinching. So you want to be careful that that pinching is being handled carefully, or you will get shading issues. It might be wrinkled. You may see your mesh appear to be stretched when you render it. So a lot of your optimizing is going to be around making your mesh, your polygons, as evenly sized and spaced as you can get them. There's an example here in the red circles. That's an interior corner, and the way that I've constructed that object is different than the one right above, where I have just 4 edges coming out of the point. On the bottom, there's 5 edges coming out of the point. And the reason that this is important to note is because when you add subdivisions and automatically add geometry, it's going to change the topology pretty drastically. So you can see on the far right, on the top and the bottom, those two objects look quite different. Okay, so now I'm going to talk about object transform operations. So when we have an object like a cube, I can move that object, I can rotate that object, and I can scale that object. But what I can't do is change the geometry of the object. For that, I would have to go and edit the object's mesh directly. Then I could move, let's say, a vertex, or I could move an edge, or I could move a face, right? And that's different than moving the entire mesh or rotating or scaling the entire mesh. So you can perform those 3 operations on both the entire object and those 3 components that comprise a polygon that I mentioned earlier. Okay, so some other operations we could perform with this object. We can subdivide it. So we can essentially add geometry using that algorithm, right? So now we have additional faces. We can inset. We can extrude. We can bevel. So I'm going to select these edges. Right now I'm beveling, and you can see this geometry is changing quite drastically, and it has new vertices, edges, and faces available to it. Okay, we can also bridge. So if I have going to join these two pieces together, and let's see, maybe I can delete those faces. All right, bridge edge loops. Now I was able to bridge those edges together. That's useful if you have a hole that you need to have the interior surface filled in with. Okay, I can merge. So let's just take this object and merge those vertices together. Now I have a different shape altogether. I can split this selection. I can separate these. So let me select all of them. If I go to mesh, separate by loose parts, so anything that's not touching will now be two different objects, right? And remember, I can edit the interior geometry separately now on these objects. Okay, there are a lot of other tools as well. Those are just some simple operations you might end up performing working on your geometry. Okay, I'm going to talk about edge flow quickly. All right, so if we let's make a long kind of rectangle here. I'm going to edit it and add a series of edge loops. So this might be considered good edge flow. And that's because, let's say I wanted to be able to deform this object, and I will put a quick deform on here so that we can see what this is going to do. Essentially, we're getting nice, even deformation with this deformer that I have on. And typically, if your edges look like they're evenly spaced, they're kind of similar in size, the edges are kind of going in the direction that you want them to go to describe the shape, that's good. So this is sort of a column lying on its side, and then we're twisting it. If you're trying to describe a face, there are all sorts of directions you would want that mesh to go. I'll add another object just to show you here. Right, so this mesh has edge loops going in all sorts of directions. So if I was to add a subdivision surface, essentially I added more geometry. We can follow these edge loops around. Let me apply this here. Okay. What we have here is chaos. Look at this edge flow. There is none. It's a nightmare. You can't use a mesh like this. You'd have to totally rebuild this or retopologize this mesh. Compared to something like this, this is a production-ready mesh for the most part. This one is something that is easy to generate, but is a disaster if you need to animate with it or deform this in some way. So that's the kind of key difference when you're worried about edge flow. Okay, so there are some things to take into consideration when you are modeling. So real world scale is really important. So if we were to want to make a chair maybe, so let's go ahead and add a cube here. This cube comes in at 2 meters. So this is taller than most human beings. It looks small on your screen, but in 3D space, it's quite large. So if we go up to item here, you can see that it's 2 meters by 2 meters. If you want to make this 3 feet tall, you can just type 3 and then apostrophe, and then now it's 3 feet tall. So you can essentially change this. It's always going to be in meters unless you change the units that your software uses. I don't recommend that. But you can type in, let's say 12 inches here, and now this will be 1 foot wide. I recommend always trying to use as close to real world scale as you can, because that's going to allow your lighting to be the most realistic. Your physics are going to be the most realistic. If things are gigantic, you can scale them down and try to get them to be more appropriate. You might be working on something that's tiny, like 0.25 inches or something. So that's 1/4 of an inch. It's pretty small, so what you might have, or what you might find as you get close to it, it starts clipping the camera here. You can adjust the clipping start and end. So we can just add another 0 there, right? So basically I made it start much closer to the camera that we're looking through to see this object. Conversely, if you're working with an object that is, I don't know, a kilometer, be careful with that. Let's see. So 1,000 meters. Okay, that's a big object. So we're getting running into some limitations here on being able to render an object that far. A kilometer, it does look like 1,000 meters is right at the edge for our camera, but we can add a 0, and now we can see that a lot better. Again, you want to be really careful with making things a kilometer in size. Typically, you wouldn't need to make something this large in 3D. That was just an example of how you might need to adjust the end clip. You do have a render camera as well. I'm not going to talk about that now since this is not a Blender demo. Okay. When you start modeling, you definitely want to use reference images. Right, now I can at least get a good idea of the proportions and scale. Right, I didn't need to know that this is different in size intuitively, and now I have a drawing to go from. So always use reference when you can. In this case, there is a front and a side view, so I'd want to have that object available to me, this image available to me in 2 directions. Right. And these are things you should keep in mind as you are working with 3D models. Okay, so that's going to wrap it up for polygonal modeling.